Okay, so last time we talked about the Schrodinger equation. We solved for the energies. We have the energy equation, and we solve for the differences in energy levels. And so those are called the transition equations because in spectroscopy, we're dealing with spectroscopic transitions. So light comes in, interacts with matter, and can cause it to excite into an excited state. That's absorption or absorbance. And then if it's in an excited state, it can spontaneously jump down and spit out a photon of light, and that's emission. And so that's really what we're talking about right now. We can get into Raman scattering and Rayleigh scattering later, but we're right now focusing on the simplest process of just a photon of light being absorbed by a molecule or being emitted by a molecule. Now we're going to start talking about the vertical axis in a spectrum. So the transition equation tells us along the horizontal axis where those peaks will show up, those spectral lines. And so then how tall are they? How strong are those peaks is the spectral intensities or transition intensities. And so light comes in and interacts with matter. Most often the matter needs to be charged. We need to have some sort of change in electric charge because light is an oscillating electric field. It's also a magnetic field, but very, very few magnetic interactions. There's a few, but mostly it's electronic interactions that are causing light to interact with matter. So like a neutron in an energy level or some sort of neutral particle, light's going to pass right through. That's also why we use, just off to an aside, neutrons are a fantastic probe for the nucleus and other things. If we can create a neutron beam, it can go right through charged matter because it's not charged. So we found out a lot about the nucleus using neutron beams. So that's kind of cool. But if we have a charged particle and light comes in and the energy of that light matches the energy level spacing, then we can have a high probability of absorption. So these are some of the requirements for spectroscopy. The particle, the matter, needs to interact with an electric or magnetic field. Yes. Is it not? Okay. Thank you. Very good. Okay. And so is it better now? It's coming up? Nope. Try this. We got a control center up here. All right. It's always impressive when it works. All right, here we go. There we go. They're much better, right? Okay, so this is the requirement. So you didn't miss anything. This was the previous 2 slides, just the intro, just talking about spectroscopy. So these are the requirements for spectroscopy. Matter needs to be charged so it can interact with the electric field of the photon of light. And then there needs to be an unequal population of energy levels. And this is most of the time the case. We have that Boltzmann distribution term, which favors the lower levels. So in general, more molecules are in the lower energy levels than the higher energy levels, just because of thermal equilibrium. And so this unequal population of levels, the more unequal it is, the stronger the signal. Because if you think about if absorption and emission have the same probability, then if the levels are 50-50, then you have a 50-50 chance of an atom going up to that energy level or an atom being emitted from that energy level. And so the signals cancel each other out. If you're trying to look at absorption, you're measuring the light before it goes through your sample and the light after it goes through your sample. And those emission events fool you. You don't detect the absorption event. So some of the light was absorbed, but just as much light was emitted. And so your sample is providing you light at the same rate, if you will, as the absorption. And so it's the difference in populations that give you good signal, especially for absorption. Okay. For a laser, we have to invert the population. We have to get more molecules or atoms in the excited state so that we can amplify the light through the stimulated emission. So a laser works with the population inversion. But either way, whether it's a laser or an absorption spectrometer, then we have to have an unequal population so that we can actually get some signal. And then third, we need a significant probability for the transition. So there needs to be a good transition dipole moment integral result. So if this is a really small number, then we don't have a significant probability for the transition. If it's a really big number, then we have a good, strong absorption band. So the differences in the absorption bands they're different because of the different integral results. And we'll see that. We'll solve for that today. You solve for it in the lab on Monday and Tuesday. So Wednesday and Thursday, you'll get to see what goes into that math today and tomorrow. So are all of these transitions possible? Let me close it. So this is just the first 4 quantum states, and look at how many arrows we have. This is, every possible state to every other possible state. On the left, we have absorption. On the right, we have emission. And so there's a whole lot of possible peaks in a spectrum. Some with short arrows, which would have long wavelengths, and some with long arrows that would have short wavelengths. And so we have all of these possibilities. We have an unequal population of states. You can see that here with the 3 charged particles in the ground state, 2 in the first excited state, 1 here, and so on. And so these are the questions that we're asking, and this is what you're solving for in lab, is the transition dipole moment integral for a pair of states. Like, let's say you got assigned n equals 3 to 4, and so you would be solving the transition dipole moment integral for wave function 4 interacting with light, which is represented by x, overlapping with wave function 3, and that would be the transition dipole moment integral for that particular arrow. Okay, and so you would do the math for that. I added a thing for the writing component in this lab where you do that in Microsoft Word, and hopefully your TA can show you some of the shortcuts to those, because it's a really powerful equation editor, but it's a little tedious to use unless you know the shortcuts. And so I posted on Blackboard a lot of the shortcuts that you can use with the slash key. So you do \psi and hit space, and it puts in the Greek character psi. And that's great, rather than trying to find it in the menus. The Greek characters are all up there, but you've got to click and search and then find psi and click it. That's way much more slower than hitting \psi space. You can hit the underscore in, and it'll put a subscript in for it. So there's a lot of little handy tips that you'll learn in using the equation editor, and that will serve you well in all of your papers, both in this class and in the other papers that you write. Let me jot this down so I can see it. Okay, good. Okay, so we have charged particles. That's a check. We have unequal populations due to the Boltzmann distribution, so that's good. And then we want to calculate the probability of these transitions. So that's what the transition dipole moment integral is actually solving. And so if the wave, how the wave functions have, different curvature, you can see them here. This ground state one has just one lobe and no nodes. And then way up here, this one has a bunch of nodes and a bunch of lobes. And so what we're doing when we multiply these functions times x is we're actually calculating these areas and seeing if they cancel out. See, we've got some positive areas, we've got some negative areas that would cancel out. And so then this, this would be in this region, not contributing to the integral and so on. And so you can look to see if these things have an overall integral that's non-zero. And so we'll look at some of those results today. And so this is our spectroscopic transition probability. This is what we mean when we're taking a spectrum. If it's a probable event, then we'll have a big peak and a lot of absorption. If it's an improbable event, then a really small peak. If it's a forbidden event, because the wave functions, when they're multiplied by each other, cancel everything out and the integral result is 0, then we won't have a peak. Even though light is matching the spacing of the energy levels, it goes right through. It's like the wave functions won't accept it. So mathematically, it's just not possible, even though the light matches the energy spacing. So that's an interesting result from quantum mechanics. This intensity, of course, we said last time that it's proportional to 3 things, B, I, and G. So B is the Boltzmann distribution, which is shown here in blue. So this is B. And then I is right here, this transition dipole moment integral. And so I've written it down here in integral form. You see the psi, the wave function for the excited state, the upper state, and the wave function for the lower state. This would be for an absorption transition. and then this is for light, that little X. Now, the way we set the problem up and so on, it's going to end up being a negative number. So if it's more and more negative, that means it's more and more intense because it's squared. So it's like you're taking the absolute value, but it's really the square. So don't be worried when you do your result and you get a negative number. The more negative it is, the stronger the transition because we square it. And then G is the line shape function, which we will get into later when we start working with Excel. At this point, we're just doing a stick spectrum. So we're just looking at the intensity and the wavelength for that transition. So the number of molecules in the lower state is determined by the Boltzmann distribution, and that's the unequal population piece. So we don't have to worry about that in our transition moment integral. We don't have any information about whether these wave functions are populated in the transition moment integral. Okay, but we get the population numbers from the Boltzmann distribution. And so this is the probability piece, this transition dipole moment. So why do we use X to represent light? Well, we have a one-dimensional box. The one dimension is the X-axis. And light has an oscillating electric field. And so this electric field vector going in this direction, you can think of it as the magnitude of that electric field. And over here, it's positive, right? And then on this side, it's negative. And so if you think about a line, like an electric field vector, with a positive end and a negative end, that has the same symmetry or the same mathematical basis as the x-axis. And so the x-axis is really just a stand-in for this electric field vector. Okay. It's also the axis for the wave functions, but we're just using it in two different ways. We have the wave function that's a function of x, and then we just have the x-axis multiplied by the wave function, and that simulates the interaction of light with this wave function. So we have light interacting with the lower state wave function, and then we're seeing if that product has a non-zero overlap with the upper wave function. So we've perturbed the lower wave function, and now can that molecule take that energy and enter into a different wave function up above? So that's why this has both wave functions in it, the lower wave function, the upper wave function, and then light perturbs the lower wave function and makes it compatible, if you will, with the upper wave function. And then the energy comes from the absorption of the photon. So there's two things going on. There's a transition in wave function, like my slinky. I had to kind of shake it a little bit. I had to perturb it to get it to go to a higher state. So I had to give it energy, and I had to give it a different shake. So the symmetry part of the x-axis is what's giving that lower wave function a bump. And then it's the energy of the photon, the momentum transfer, that's giving it the boost to get up to that higher energy of that upper wave function. So, how can we get that maximum value of light interacting with our wave function? We just put that electric field on the x-axis. It also has a weak magnetic field at 90 degrees, but we really don't do anything with that. And so if we take a snapshot of that maximum electric field, it would be, mostly positive on the right end I have here and negative on the left. And so we're just going to use that x-axis as our electric field standing. So here's our problem, the way we set it up. Now, I've done it for the general case and posted that. So essentially, you have the whole result for you. All of the calculus, all of the trig substitutions, integration by parts, put up there in color so you can follow through the problem. But I just have you do it for particular states. So like if you had the 3 to 4 transition, it doesn't matter which one's the bigger one. So maybe you have 3 here and 3 plus 1. So this would be 3 plus 1. So you're going from 3 to 4. Then wherever you have n, you have 3s, and n plus delta n, you have 4s. So that's your problem if you were assigned 3 and 4. Okay. And then you do the calculus with those specific numbers in there, and it's a lot easier really when you don't have that delta in there because it creates a kind of a messy bit of calculus or algebra. But anyway, I solved it for the general case, and you can solve it for the specific cases. Now, you might have a situation where you get down and your delta n is even and your result is 0. That's okay. That's an answer. So what you have is a forbidden transition. Okay. And so about half of you probably will have even delta n's, and you're going to end up with the answer of 0. But you need to sort of justify in your Excel, in your Word document, why it's 0. And you'll see that in my document. So you can kind of go through that and follow along side by side, and you do your work, but you can refer to mine. Okay. So after 4 pages of calculus and algebra, we get this result. All right, so this is the end result here, where all of these constants came out front due to integration and so on. And we end up with these sine functions turning into cosine functions, and we have this difference between cosines in both of these terms. And so what we need to do is we need to look at the cosine curve. Notice at 0, 2 pi, 4 pi, cosine equals +1. And so there's a difference between even multiples of pi and odd multiples of pi. At 1, 3, 5, etc., cosine equals -1. And so this is where our selection rules come from. So when delta n is even, this cosine piece here, we have a negative, but it's still an even multiple of pi. This cosine will give a 1. And if this cosine gives a 1, we have a 1 minus a 1. And so this piece goes to 0. What about over here? We have a 1 on this side now, minus something over here. And so we have, when delta n is even, we have a 2n here. So whatever our lower state is multiplied by 2. Well, that ensures that that piece is even, because an odd number times 2 is going to be an even number. So this piece is even, and when delta n is even, you have the sum of 2 even numbers. That's never going to be odd. And so when delta n is even, we have an even multiple of pi, which gives us a 1, and that means this piece goes to 0 as well. It'd be really kind of odd, it'd be strange if one of these terms was 0 and the other was 1 and then swapped the other way. But, I mean, that could happen too. But in this case, when delta n is even, then this whole term goes to 0. And so we're saying that the intensity is 0 for all even jumps. So 1 to 2 is a delta n of 1. That's odd. But 1 to 3 is changing 2 energy levels. So it's jumping 2 quantum states. And the probability of that transition is 0. So it can't do that. A particle in a box can't do that. Now, there may be other spectroscopic systems, electronic transitions, and so on, but for our particular system, the one-dimensional particle in a box, the light cannot cause a particle in a box to jump 2 states. It can jump 1, or it can jump 3, or 5, or so on. Let's look at the odd case. So when delta n is odd, we have odd multiples of pi, and this becomes a -1 and a -1. So this piece here becomes a 2. Okay, and then that 2 comes out front. And so then we have a constant there. And then over here, when delta n is odd, we have an even number, 2n, plus an odd number is going to give us an odd result. And so we're going to always have an odd multiple of pi, and that's going to be a -1, but this is a negative. So it's going to be 1 minus a -1. Is that right? Yeah. And so then it's going to equal 2. And so then that 2 is going to come out front. And so we end up with this result here. So it's 0 when delta n is even, and those 2's came out front. One of these terms became negative, the other became positive whenever we had the odd multiples of pi, and so we have this difference in the middle. And then this whole thing is squared, so it doesn't matter if it comes out negative. Okay. And that's when delta n is odd. So this tells us our non-zero probabilities. And if we know the box length and we know the quantum states, we can calculate the intensity of the transitions. So this is a fantastic result. We can now know how tall the peak is, and with the transition equation, we know where the peak will be located. So this gives us our selection rules. The change in quantum number is going to be plus or minus 1, plus or minus 3, plus or minus 5. Notice the negative, the drops, the emissions are the same intensity because the delta n's are always squared. So whether delta n is positive or negative, you're going to get the same intensity. So that's also a nice result that we get out of this calculation. Do you see what I mean by selection rules? So everybody pay attention to this. The selection rules tell you the allowed transitions. So we identified the ones that were 0, but the selection rules are telling you which peaks are allowed. And so we can come over here and look now. This is the results plotted for a box length of 200. So from minus 100 to plus 100. And these are all of the probabilities. And so these jumps of 2, so 1 to 3 is 0, 2 to 4 is 0. So that probability is 0 even if it's populated. The absorption and emission probabilities are equal. So in this case, going from 2 to 3 is 1,514, and going from 3 down to 2 is also 1,514. And then skipping levels is less probable. So that's interesting. So look at this. Going from 1 to 2, so a delta n of 1, delta n equals 1, is a huge probability, 1,298. And going from 1 to 4, it's allowed, but it's only a probability or an intensity of 8.3. So really small intensity for that peak. This is called an overtone. Okay. We'll look at some of these vocabulary words in terms of these transitions in a minute. Notice where, delta n equals 1, you see that's going to be in the denominator over here. So the change in energy levels is in the denominator. So when delta n is 1, you have the smallest denominator, so you have the largest fractions. If we go to 3, delta n equals 3 or delta n equals 5, you see it's in the denominator and it's squared. And so we've got a huge drop in intensity. And so this is, we've calculated these I values here just now. And those are these intensities here. Now, if we look at the transition equation, that will tell us the locations of the peaks. So notice how this piece right here deals with the vertical axis. The transition equation is what tells us about the horizontal axis. So let's go back and revisit those. This is the transition equation for energy. So these are the energy differences. This is the frequency differences. And these are the wavelength differences. So this is the wavelength equation. I put up a homework set last night as well. And some of the later problems are for you to calculate the transition equation, the transition wavelengths. You'll do that for your lab too. And you'll calculate the intensity so that you can do a stick spectrum. And so here's what we call a stick spectrum. Now, I just have you plot 2 of them because I didn't want you to have a tedious time of drawing a bunch of lines, but you just plot 2 of your intensities and wavelength values. Now, this is done versus transition energy. This is also proportional to frequency. So a frequency spectrum would look like this. Equally spaced lines if it's plotted versus frequency. Okay. Now frequency is equal to c over lambda, and sometimes we plot it what we call wave number. So wave number is just equal to 1 over lambda, and when specifically when the wavelength is in centimeters. And so that's equal to centimeters to the -1 is a unit. So infrared spectra are typically plotted versus wave number. You've seen that in organic, right? A 3000 wave number, CH stretch, a 1600 wave number, carbonyl stretch. And so these, the energy equation converted, say, to frequency is going to give you things like this. And for the particle in a box, we would have equally spaced spectral lines. You can see that in the equation. This first one is the fundamental. So that's the the 1 to 2 transition. If we have thermal population in the excited states, then we have hot bands. So this word is telling you something about that. Hot bands means thermally populated. This is also why our spectroscopy gets a lot cleaner when we cool things down. And sometimes we'll do spectroscopy in like cryogenic temperatures, liquid nitrogen temperatures, or even liquid helium temperatures, because it gets rid of all of the hot bands, and you just have a single fundamental. Okay. And then these are the overtones. This is the delta n equals 3 and delta n equals 5. I don't have any 7s on here, but they would be allowed as well. But you see how much smaller their intensity is. So this was 1200, close to 1300 right here. And this one here, the first overtone was 8.3. Okay, so plotting those on the same graph, I mean, you can do it, but the 8.3 is really just right on the axis when you're plotting 0 to 1300. So this is the energy equation. Notice how when we say it's equally spaced in n, this is this delta E. So this is the change in energy. So that's the change in energy levels. This is the spectral lines that we're plotting. It's linear in n. So when I go from n equals 1 to n equals 2 to n equals 3 to n equals 4, I just have another unit of this constant out front. And this constant, as I said before, is where the good stuff is. This is where the mass is, where the length of the box is. This tells us the physical properties of the system. So I could take these peaks, and if I peak picked them, and you'll do this in lab in about 4 weeks, if I assign quantum numbers to these peaks, and I do a linear regression to get the slope of those quantum numbers, notice this looks like a linear equation, and this is the slope. Y equals m, and this piece right here is x. And so if I had a column of n plus 1/2, and I had a column of delta e's, or in this case, delta e's, then I could find the slope between the column x and y, and that slope would be h squared over 4ml. And I could pull the length out of that constant, and I could pull the mass out of that constant. And that's what we're going to be doing for the carbon monoxide molecule. This is the equation for the overtones. Notice they're also linear or equally spaced in n. It's linear in n, but we have this factor of 3 here. And so the spacing is bigger, and you can see that. It's 3 times bigger. And then for 5, it's like 5 times bigger. So here is what we would call an assigned spectrum. So if you had an experimental spectrum like this and you put in the quantum number transitions, that would be an assignment, a spectral assignment. So you give assigned quantum numbers to every transition in the spectrum. And that's what we're going to do for carbon monoxide and for iodine. And so we have the same transition equations. Here's the 5 one. You see it's at 5 times the spacing. So this gap right here is this piece. Whereas this gap here is this one. And then this tiny little gap here is this one. So if we were doing this backwards, this is a simulated spectrum, but if it was experimental, if we were doing this backwards, then we could use this spectral assignment to get the physical properties of our system. So these are the things that are transferable to real spectra. If you have a real spectrum with real peaks and you know the quantum behaviors for that, or you make an assumption that you do, and you assign it according to a certain assumption, then you get the physical properties out. And so that's what we do in real life. Okay, let's plot it versus wavelength. What do you see? Why? Look how different it is. What's the most prominent thing? I'd like to get your ideas of what you see in this spectrum. What's the thing that stands out to you the most? I heard some mumblings.
Well, I said it looks backwards.
It does look backwards. Yeah, it is. It's flipped because it's 1 over the quantum numbers now. And so that causes something else. What else do you see? It looks flipped.
The spacing between the lines.
Yeah, the spacing's no longer constant. In fact, it's an inverse relationship. So notice how they're all crammed to 0, right? And so this transition wavelength essentially is 1 over delta E, right? And so then all of those constants are upside down, and it's an inverse relationship to N. See, it's proportional to 1 over N. And so as N gets bigger and bigger, the wavelength gets smaller and smaller. And so we see that as N gets bigger and bigger, the wavelength gets smaller and smaller, but there's a limit, right? It's capped out at 0. So it's never going to reach 0, but it's going to get really close. And this does a couple of good things. One, it separates the fundamental from everything else. And so a lot of times if we have really broad peaks that are hard to resolve, we prefer to plot them versus wavelength than versus frequency. And so that's why UV vis is plotted versus wavelength. Because in electronic spectroscopy, the peaks are really broad and they overlap. If you plot them versus energy, they're hard to resolve. And so we plot them versus wavelength so that fundamental is stretched out away from all of the other peaks. And then they all sort of create this, what we call like a blackout or a solvent window. I mean, they cut off wavelength, and you just don't see any information at the lower wavelengths. And if you've ever taken a UV vis spectrum, there'll be a spot where you might have a few peaks, but then pretty much the absorbance goes to infinity. And that's what's happening down, in the UV region. It just starts to cut off all of the light because there's so many transitions over here. All of the hot bands, overtones, they overlap with each other and they absorb every kind of photon that you can put in there. Okay, we could still use this if we just find the fundamental. We just put a 1 in here for N. And you put a 1 in for N, and you end up with this constant. And so even with just a single spectral peak, if you apply this model to it, you could solve for the mass, you could solve for the wavelength or the length of the box and so on. Now also notice that the wavelength is directly proportional to mass. And so if I increase the mass by say 10%, then this is going to get bigger. The wavelength is going to be red shifted by 10%. It's proportional to the length squared. So if I make a small change in the size of my system, I'm going to have a huge change in wavelength. And then here's for the overtones. You can see that essentially we have, this factor of 3 in the denominator, and so it's dropped down into the small wavelength region. We have a 5 in the denominator for the second overtone, and so it's even smaller. Here's the spectral assignment, and notice how the peaks get so close together you really can't assign them very easily. But I assigned all the way up to 7. So this is, again, just to reinforce where these peaks come from. This is the transition dipole moment intensity. This is I 1 to 2, which is proportional to that transition dipole moment of psi 2 x psi 1 squared. Okay, and so we squared that. That's that y value, the vertical axis value, and then down here, this is that transition wavelength equation where we put in 1 right here, and the mass of the electron and the length of the box and everything, and we end up with, so this was right here was 200, and this was the mass of the electron, 9.11 times 10 to the minus 31 kilograms. And the speed of light, 3 times 10 to the 8 meters per second, Planck's constant. And then because of the units, and when you're calculating this, you're going to end up with angstroms squared. That's not nanometers, okay? You're going to have to cancel one of those angstroms to meters to help cancel one of the meters in the Planck's constant, and then you're going to have to convert the other angstrom to nanometers. And so there's 10 angstroms per nanometer. So you're going to have to multiply that by, I think, 10 to the minus 11. But you work out the units, and then you'll get nanometers. And so you'll be able to see the wavelength, the transition wavelength. Okay, so that's a simulated stick spectrum. I have you calculate these two right here. So you're drawing by hand a stick spectrum with your calculation here, the wavelength. You're calculating two wavelengths here and here. You're calculating two intensities there and there. You can use this equation back here to calculate those intensities. Like you did the full calculus, but when it comes to the very end, when you need to calculate transition wavelengths and more intensities, go ahead and use this equation right here. And I think I have it for your box. It's 5.5 angstroms. Notice there's no mass in the intensity equation. There's only box length really in the change. So you put in the quantum number. If you're going from 1 to 2, that's the fundamental. If you're going from 2 to 3, then you put a 2 here in for n, and a delta n of 1, and then you put in the 5.5 in for L, and you can calculate the intensity. You square it. Don't forget to square it. You'll realize it's a negative number, so you'll want to square it. Okay. And so that's how you do it. You can calculate then a stick spectrum, and it will look just like, well, not just like, but it'll be similar to what Schrodinger did to earn the Nobel Prize. So he did that stick spectrum of hydrogen after all of his calculations, and it matched so well that they basically said, "Ah, he solved it." Okay, so let's reinforce our concepts by doing a Kahoot. Okay, just a minute while I get this set up. Okay. Okay, there's the game code. I wonder why the music's so quiet. There we go. It's always fun in October. They do a Halloween theme and it's spooky music. Okay. If you're still trying to get in, just say, "Wait for me." Anyone? Okay, it looks like we've got everybody. Let's get started. Okay, absorption and emission have the same probability, which means they have the same transition moment integral result. True or false? Hey, good job. That's also one of the papers of Einstein. He solved the actual transition probabilities, and he showed that they're the same. They're called the Einstein coefficients, actually. Number 2, transition equation is related to which axis of the spectrum? Look carefully at it, the transition equation. Oh, good. I was expecting more people to have trouble with that. Okay. So the transition, so we have transition stuff everywhere. There's the transition equation and the transition dipole moment integral. So let's see. All right, rising stars. So the transition dipole moment integral affects which axis of the spectrum? This is that really long calculation that you're doing in lab, and it's the one that involves the overlap of the wave functions and light. Yay, good job. Okay. Ooh, a lot of people moving up. The transition equations tell us about the spacing of, this one's tricky. It's almost a 50-50 split. Okay, so these are the transition equations, and this constant out front is going to be the spacing of the spectral lines. So how far apart the peaks are. Okay, now they use the spacing and the energy levels to come up with this equation, but the result tells us about where the spectral lines are. So it's telling us about the spacing and the spectral lines. Number 5, the energy equation tells us about the spacing of, so fast. Energy levels, exactly. Oh, one shy of perfect score. Sorry. So we have this energy level here, energy equation, and it's telling us the spacing. So if we change the quantum number, then it tells us the spacing and the energy levels. Okay. And so we'll use this in the homework. I'll say if we, double the length of the box, what happens to the energy level spacing? If we increase the mass or if we increase the quantum number, and it can tell you how the energy levels are spaced. All right, let's see how we did. Okay. Nicely done. And for gold, we have very good. Well done. And some runners up. Okay. Well, to be honest, we are done a little early today, so I don't know that people will complain. If you didn't get into the Kahoot, you can come forward and I can get you on the roster so that your attendance is logged. All right, good.